This is the first lecture of chapter 17, a new chapter. In this chapter, we will be looking at aromaticity, aromatic compounds, and at the end, we will look at reactions that involve aromatic compounds. But in this presentation, the following will be covered. First of all, we'll look at aromatic compounds. What are aromatic compounds and what's so unique about aromatic compounds? Next, we will review the nomenclature of aromatic compounds. Then we look at the characteristics of aromaticity. What determines aromaticity in a molecule? And lastly, we'll apply those characteristics that we have defined here to determine which molecules are aromatic or not. Okay, so let's go. So benzene is an aromatic compound, and we have often heard the saying that compounds have a particular aroma. So aromatic compounds are typically known for their aroma. Benzene is an aromatic compound, and we'll use that as an example in our discussion. So here's benzene, the structure of benzene, C6H6. So what I wanted to point out here is that this benzene structure is in a lot of different molecules, different compounds that are used in everyday life. Benzaldehyde is an ingredient in some fruits and nuts. Here is vanillin. Here is the benzene molecule here, or the benzene part of the molecule. Vanillin, main ingredient in vanilla. Cinnamaldehyde, here again is that benzene structure, aromatic structure. Here's another one. Here's this is what's that? Aspirin. Here's the benzene structure, and here's another one. This one has two benzene structure. This is an antidepressant. So the bottom line is that this benzene structure here is a very common feature in a large percentage of organic molecules. So let us examine that. But before we do that, let's look at the nomenclature of substituted benzenes. So here's the benzene. You'll have to recognize the benzene part of the molecule. Here it is. So this is a substituted benzene, disubstituted in this case, two bromines bonded to it. Now how do we name that? The bottom line is to identify the substituents and add the word benzene to it as shown here. So in this case, this is benzene. Here's the benzene portion of the name. And there is a bromo and another bromo. So we know it has to be a dibromo benzene. Then we'll have to indicate the location of these two bromines. Then positions number 1 and position number 3. So it's a 1,3 dibromo benzene. Here's another one. This is the benzene ring right here, and it has a bromine substituent and a nitrous substituent. So which one goes first? We go first in terms of the alphabet. So bromine goes first, followed by nitro. So this is a 1 bromo and a 3 nitro, because the nitro group is in position number 3. Notice it's not 5. You go the shortest route in the direction of the substituent, and of course nitrobenzene. Another example, benzene ring is right here, bromine and a methyl group. So it becomes a 1-bromo because B comes before M. So therefore it's a 1-bromo, 2-methyl, 2 because it's in the second position from the bromine. And the last one here is 1,4-dinitro. Notice again, dinitro, because it's 1, 2, 3, 4. That's the relationship, and of course ends with the word benzene added to it. As you know, in organic chemistry, we have different names have been used over the years. And here's an example of the common name of some molecules, or the common names of some molecules gaining its way into the nomenclature of molecules. So here's one. If there's a benzene ring and it has an OCH3 bonded to it, it's known as anisole. Here's another one. If there's a benzene ring and it has an hydroxy bonded to it, it's known as phenol. So this entire molecule is known as phenol. Here's another one. Aniline has a amino group bonded to it. So this entire molecule is known as aniline. And another one, toluene, common solvent, has a methyl group, so this entire molecule here is known as toluene. Benzoic acid, we're familiar with that. We've seen that quite a bit throughout our course so far. It, of course, has the carboxylic acid functionality bonded to the benzene ring. So therefore, this entire molecule is benzoic acid. Last one here is benzaldehyde. It has an aldehyde functionality bonded to the benzene ring. So that's benzaldehyde. As I mentioned, these names, or these common names, have been used in naming molecules that have the benzene structure. So let's look at those. So if we have a molecule like this one right here, what you need to do is to observe one of those root names, one of those common names. So here is toluene. So that becomes toluene and not methylbenzene. So if it's toluene, the relationship is 1, 2, and 3. So therefore it's 3-nitrotoluene. Let's look at another one. If you got this to name, you should recognize this as the aniline root. So here is the aniline root, and there is a nitro group, so it's a 3-nitroaniline. Don't forget the numbering, because it could have been here, and that would have been a different molecule, which would be 2-nitroaniline. Here's another one, phenol. This is right here. And of course the nitro group, so here is the phenol part of the molecule, which is right here, and the nitro is right here, and the 3 because it's 1, 2, and 3 location. So this one, the root is not shown, so you should recognize this as the benzoic acid. So it becomes 1, 2, and 3 bromo and benzoic acid. This is the benzaldehyde. So here's the benzaldehyde portion that you should recognize. So this becomes 1, because that will now determine the name of the molecule. In this case, since it's symmetrical, you can go in either direction. So 1, 2, and 3, 4, and 5. So it's 3,5-dichlorobenzaldehyde. And lastly, we have here, this is the anisole portion of the molecule, and in position number 4, so it's 4-nitroanisole. So again, if you named it as methoxy nitro, that would be 1-methoxy for nitro benzene, that would not be wrong. It's just that we prefer that you recognize that feature in the molecule. Let us look at another system of naming molecules, and it's based on the relationships. So it's really the nomenclature of disubstituted benzenes, two substituents on the ring. Based on the relationship of these two substituents, we have a terminology that's used to describe this relationship. So if it's a 1-2 relationship, where this is 1 and 2, it's described as an ortho relationship, or an O. Instead of saying a 1-2, we just say ortho. If it's a 1-2-3, if it's a 1-3 relationship, it's described as a meta relationship, or a M. And of course, if it's a 1-4 relationship, as shown here, it's described as a para. So we'll use these terms frequently as organic chemists to describe the relationships between two groups on a molecule. Of course, if you go in this direction, this is still a 1-2, as shown here, or a 1-3, as shown here. So it's still a meta or an ortho, depending on the relationship, 1-2 or 1-3, and of course para being a 1-4. So let's apply that. So here we have toluene. Hopefully you recognize the toluene portion here and the nitro group here. So that would have been a 1-3 up to now. But now we know a 1-3 relationship is also a meta relationship. So we can name this molecule as meta-nitrotoluene. Of course, if you did 3-nitrotoluene, that's still a correct name for that molecule. Same here. Meta-nitroaniline. Meta. Sometimes you just see M to describe the meta relationship. And of course, the last one we have here is a nitrophenol. Here's the phenol again. So don't forget, I should have put another example here, but if you had here, let's see if we can draw that, OH. And if we had put the nitro group here, and of course make sure that it's aromatic, this would be the phenol, so it would be an ortho. So it's O nitro phenol. So again, you should be able to apply the concepts that we have looked at in the previous slide in terms of the ortho, meta, and para system of describing the relationships between two substituents on a ring. Let us look at benzene now. So the question that we're asking is, why is benzene such a unique molecule? Why is it so unique that it's used as a solvent? It's not very reactive, that's why it's used as a solvent. And why is it so common in most of the organic and pharmaceutical structures? So let us study the structure of benzene and see if we can understand aspects of benzene. So here's the formula, C6H6. And here is a representation of that C6H6. It was discovered that the best way to represent C6H6 is in a cyclic form, because you have 6 carbons and 6 hydrogens. And we cannot violate the rules that we've learned before in terms of bondings to carbons. So this is the best arrangement we have. So these carbons here are sp2, where we have an unhybridized p orbital with 1 electron in each carbon. So we have 6 carbons that are sp2, and 6 carbons have an p orbital that's unhybridized with 1 electron. So this is what it looks like. Okay, what we do know is that all the bonds here, these carbon-carbon bonds, we do know that they're equal. So in other words, they're not alternating between double and single. So in other words, what we're saying here is that these 2 electrons, for example, they don't bond here to form a pi bond. And these don't bond here to form that pi bond as we have studied before. And these don't bond here to form that pi bond. So this method would imply that this would be a double bond, and right here would be a single bond. And this would be a single. So that's one model that's been proposed for this. Of course, you can do an alternation of that, where this would be now your double bond, and here is your single bond. The question now is that correct? It turns out that that's not correct, because we do know that the bond length here for the double bond would be shorter than that of the single bond. But we do know from experimental evidence that all the bond lengths here are the same. It was shown by Kekule, or proposed by Kekule, that there's a rapid equilibrium in 1,2-dichlorobenzene, where this is now a double bond, and over here it's a single bond. So that was his proposal to account for the bond lengths being all the same, a rapid equilibrium. But now we know that's not true. That's not true, because we have developed spectroscopic techniques to show that this bond length here is the same as this bond length here. So we got to go back and look at the structure and come up with a different model. So let's go back. So this is what we had before. So one way of describing this is that all these 6 electrons are in constant motion throughout all 6 carbons. It's like they're moving rapidly throughout these 6 carbons. Of course, as you know, there are 2 planes to a p orbital, they're above and below. So here's the representation. These 6 electrons are moving up, above, and below the ring. Another way of putting that is the probability of finding those electrons are above and below the ring equally. It's like they're moving so fast. So this represents here a better description of the benzene molecule, because if these 6 electrons were delocalized constantly throughout the 6 carbons, then the bond lengths here would all be the same. So this model here explains much better the structure of benzene. Now comes the problem. How do we draw that? Because of course, as you know, we have to draw these representations in 2 dimensions on paper. So we can do this if you're a good artist, but as you know, that takes time. So what's accepted now is this format, looking like the Kekule structure, but it's used just to represent the benzene molecule, because it's very difficult to draw this every time. You can also draw this also. Notice, because this is a double bond here, and here it's a single bond. So it's, over the years, it's been accepted, even though it's not a very good description of this molecule, it's been accepted as the structure of benzene. Lastly, most chemists tend to prefer this representation. 6 carbons in a ring and using a circle in the middle, to represent these 6 electrons here moving in rapid succession around the ring. So whichever one you use, this one, or this one, it is correct. Or should I say, it's an acceptable representation of benzene. Let's continue our discussion in terms of the uniqueness of benzene. I mentioned earlier that benzene is very stable. It's used as a solvent in the organic lab. In other words, it will not react readily with other compounds. So the question is, why is it so stable? Because you would expect it to be fairly reactive because of those pi electrons, being a Lewis base, but it's not. So let's look at if we can get some idea of its stability based on some reactions. We do know that the hydrogenation of molecules can give us ideas of the relative stability because there are exothermic reactions. So if you take cyclohexene, 1 double bond, reacted with hydrogen in the presence of a catalyst, you get cyclohexane and heat liberated, 28.6 kilocalories per mole. If you take 1,4-cyclohexadiene, which is a real molecule, so this experiment can be carried out or has been carried out and reacted with hydrogen, you get cyclohexane, the same molecule, but over here you get twice as much heat liberated. So the indication here is that 1 double bond gives 28.6. 2 double bonds would give twice as much. So the implication is, if we had this molecule here, which we call hypothetical 1,3-cyclohexatriene, hypothetical, because it's not a real molecule in terms of this analysis, it's predicted that the heat liberated for this reaction would be 3 times as much as for the single double bond. So I don't want to confuse you. So what we're doing here is we're trying to estimate what is the energy that's liberated if we should predict the amount of heat liberated based on these 2 models here, these 2 reactants. So it's 85.3. If you go in the lab and you actually do the experiment with benzene, you actually get 49.8, far less than expected, far less. So of course, as you know, the amount of heat that's liberated gives an idea of the stability, because it liberates, it's an exothermic reaction and liberates far less than expected here. This molecule, benzene, is very stable. Let's close this. Let us look at this concept in terms of the energy profile. Okay, so let's look at this in terms of the energy profile. Why is benzene such a unique molecule? As I mentioned, they are exothermic reactions. So here is the hypothetical cyclohexatriene. It goes to the product cyclohexane. And here's the benzene. It liberates much less heat and goes to the same product. So therefore it is stable or lower on the energy diagram compared to expected. The difference is 36 kcals. So we say that Benzene is more stable than expected by 36 kcals per mole. You need not remember that exact number, but what you need to remember is that it is more stable than expected. That's why it can be used as a solvent. So, conclusion from this: aromatic compounds are more stable than expected, as we stated here. So, aromatic compounds, including benzene, are more stable than expected when compared to a hypothetical molecule. Okay, so let's concentrate now on, can we determine other characteristics of aromaticity, so that when we look at a molecule, can we determine if it's aromatic or not? So here are some characteristics. We have here 5. So the first one we have already discussed. The energy must be lower than the hypothetical system. In other words, it must be stable. And that's again from experimental. The other one is the structure must be cyclic and conjugated. So we'll discuss each of these in the next slides. An aromatic compound must follow a rule known as the Huckel rule, which is the 4n plus 2 electrons. We'll describe that. Another is that each atom must have at least one unhybridized p orbital. We'll say more about that. And lastly, there must be complete overlap of p orbitals so that the electrons can move freely throughout the conjugated system. So let's discuss each as we go through here. All right, aspects of conjugation. So they must be cyclic and conjugated. So here is remember conjugation here just means alternating single, double, single, double. So here is a conjugated system because it has double, single, double. And it is cyclic. So it's possible for this to be aromatic. Of course, we know that's benzene, so it is aromatic. But let's look at this other system. This is conjugated because it has a double, a single, a double, a single, and a double. But it's not cyclic. So this molecule here is not aromatic. Here's another example. This has a double bond. It is cyclic, but it's not conjugated. So this molecule is not aromatic. So of the 3 molecules shown here, only this one meets the criteria so far to be aromatic. Let's look at another characteristic. The electrons that are in conjugation must follow Huckel's rule, which is 4n plus 2, where n is an integer. Sounds like a lot, but let's explain that. So we need to first of all find the number of electrons that are in conjugation, or the pi or the p electrons. So here we have a double bond which has 2 electrons. So here we have 2, here we have 2, and here we have 2. So we have 6 pi electrons in conjugation. Based on Huckel's rule, 4n plus 2 equals 6. If n is an integer, such as a counting number, 0, 1, 2, 3, 4, then that molecule meets this characteristic of being aromatic. So as you can see here for this molecule, which of course as you know is benzene, n is 1, so therefore it has met so far all of the characteristics to be aromatic. Let's look at this other molecule here. Here is 2 and 2, 4, and these 2 here, it will be part of the aromatic system, or could be. So let's check. So we have 2, 4, 6. So the same equation we have to use. And we have 6 electrons. N is an integer. So therefore, so far, this molecule here has met all the characteristics to be aromatic. Let's look at this one. This has 2 electrons here, pi electrons, 2 here, 2 here, and 2 here, which means 4n plus 2 equals 8. We solve for n, and we can see here n is 1.5, 1.5, not an integer. So therefore, this molecule here fails the criterion of Huckel's rule. So again, to be aromatic, it must pass all of these criteria or characteristics that we are discussing. So this is cyclic. The electrons are, the bonds are in conjugation, but it fails to meet Huckel's rule, so therefore it is not aromatic. Let's go on. Each atom must have at least one unhybridized p orbital. So we know these are all p orbitals bonded here because it's sp2, so that meets it. But over here, however, this is cyclic, has conjugation, because double, single, double, single, double. But over here, these carbons are sp3, which means that they do not have a vacant, unhybridized p orbital. So therefore, these 6 electrons here, even though they meet Huckel's requirement, they cannot delocalize throughout the ring because these carbons here, they do not have a p orbital for the electrons to be delocalized because they are sp3. So this molecule here is not aromatic as shown here. Let's look at the orbitals must overlap. So of course, as we know, p orbital, p orbital, p, p, and p are here, 6 electrons, 1 in each. So therefore, there's a complete overlap here for benzene. Let's look at this one. This is an sp2, and it has, again, I'll just draw it just to show you, a vacant. Why vacant? Because it is a cation. It has a positive charge, which means that there are no electrons in here. So, this means that this has met the requirement to have the electrons, these electrons delocalized throughout this ring. So it's a ring, it's conjugated, and these 6 electrons, which meet Huckel's rule, by the way, can be delocalized throughout this cyclic system. So, based on the requirements so far for aromaticity, this would be aromatic. But for the time being, we're just looking at it having a carbon, which is sp2, and a p orbital that the electrons can be delocalized throughout. So let's look at examples here of polycyclic. So let's try and apply some of the characteristics that we have studied so far, because we have covered all 5. So polycyclic here just means many cyclic. So here we have 2 cyclic rings. Let's see if it meets Huckel's rule. We have 2 here, 2, 2. Over here we have 2 and 2. So that makes 10. So 4n plus 2 equals 10. N is an integer, so therefore that meets Huckel's rule. Is it cyclic? Yes, it is. Are the electrons all delocalized throughout? Yes, they are, so therefore that's aromatic. Same here. You'll count and see that the number of electrons for this system here, anthracene, is 14, which makes N an integer 3, which means that this is aromatic. And let's look at this one. Same 14 electrons, but notice again, all of the carbons are sp2 hybridized, which means that all of these carbons here, they have a p orbital, unhybridized p orbital, so that electrons can move through those orbitals, and N is 3, which means that this is an aromatic molecule. Let us look at heterocyclic compounds. So here is a heterocyclic compound, pyridine, because it's heterocyclic because it has nitrogen here. Of course, you may recall that hetero means different from carbons. So let's look at this. This is a nitrogen. You will recall this is an sp2 nitrogen, which means that it has a p orbital here with 1 electron, and it also has an orbital here, sp2, with 2 electrons. But these electrons here are orthogonal, or they are perpendicular to the plane of these 6 electrons that are in circulation. Here's a representation. So the 6 electrons of pyridine are in circulation, and the pair of electrons that are shown are orthogonal. Another term for that is they are perpendicular. So these 6 electrons are not involved in, these 2 electrons, pardon me, are not involved in these 6 electrons that's being delocalized. So therefore this molecule is aromatic. We looked at this one earlier. So let's see. This is 2, 4, and 6. We know that this is we have seen that this is sp3 hybridized, but because it can get all 6 electrons here to be in conjugation in that ring, this nitrogen is hybridized or rehybridized to be sp2, putting these 2 electrons in that sp2 in that p orbital, so we can have complete conjugation. Let me say that again. So this nitrogen here, there's a rehybridization to be sp2, which has a p orbital with 2 electrons. These 2 electrons. So we have now 2, 3, 4, 5, and 6 electrons that are now in conjugation and can circulate above and below the ring. So therefore this molecule is aromatic. Let's look at a last example here that has a heteroatom, sulfur. Much larger, but it still has here a pair of electrons and another pair of electrons. So what happens here is we have 2, 4, and 6 electrons. We know that sulfur is below oxygen, so we'd expect it to be sp hybridized, putting these 2 electrons in the sp, did I say that wrong? It's sp3 hybridized, so we'd expect these 2 electrons to be placed in the sp3 orbitals. However, because we can put 2 electrons here in conjugation with these other 4 and gain aromaticity. Remember, aromaticity here means stability, lower in energy. We have here the system. Let me say that again because I think I used the term that I had to correct. So the sulfur here, it's below oxygen on the periodic table. So you may recall that water is that, and we have here 2 unshared pair of electrons. So we know that this oxygen is sp3, where we have bonds here using up 2, and these 2 electrons and these other pair of electrons would go in the sp3 because there are 4 sp3 orbitals. For sulfur, it's the same concept here. But for sulfur, if this sulfur is rehybridized to be sp2, it will put 2 electrons in the p orbital, and the other 2 electrons will be in the sp2, so that we have here a complete movement of electrons over the ring, making thiophene aromatic. So bottom line is, thiophene is aromatic. Only 2 of these electrons on sulfur are involved in aromaticity, and the other 2 are not. They're considered, they are orthogonal or perpendicular to the plane of the aromaticity. Let us look at another example here, imidazole. So let's apply that. So this nitrogen here, as we said earlier, where we'd expect it to be sp3, with these electrons in one of those sp3 orbitals. However, we can get these 2 electrons here to be in conjugation with these 4 by rehybridizing this nitrogen to sp2, where these 2 electrons are now in our p orbital. So we have a nice 6 electrons that are in conjugation. Let's look at this nitrogen. This nitrogen here is similar to that of pyridine that we discussed earlier, sp2. So these 2 electrons here are perpendicular to the plane and are not involved in aromaticity. It's just these 6 right in here. So the bottom line is, whenever you get a molecule, to determine if it's aromatic or not, you will have to carry out a careful analysis of all 5 criteria that we discussed to determine if the molecule is aromatic or not. So let us conclude by looking at some molecules. So the question is, which of the following molecules or ions, because we have positives and negatives, are aromatic? So let's look at this one. This is there are 2 electrons here, 2 electrons. All the carbons are sp2 because this is a carbocation right here. So they're all sp2. And don't forget, if this is sp2, it has here a p orbital. In this case, since it's a carbocation, it's vacant. So this has 4 electrons. That may say something about the Huckel's rule. Let's look at this one. This is sp2 again. Don't forget, if it's sp2, it has a p orbital. And in this case, it has 2 electrons here because it's an anion. Anion here means 2 electrons. So now we have 2, 4, 6, and 8 electrons. That's telling us something about Huckel's rule. 8 electrons, they're in conjugation, it's cyclic, but we'll have to consider Huckel's rule. Here's another one, 2, 4, 6, 8. Remember, this is a nitrogen, and it can hybridize to put these 2 electrons in a p orbital. So we have 6 electrons here, and we have a p orbital that can accommodate those, and it's cyclic. Let's look at this one. This is cyclic, 2 electrons here, but this carbon is sp2 bonded to an oxygen, but since oxygen is more electronegative than carbon, these electrons in here would be closer to the oxygen than the carbon. So we can consider there are no electrons right here. So this would be 2 electrons in this cyclic system right here. Let's look at this one. We have 2, 4, 6, 8, 10. it has an unshaded pair of electrons here, but since this nitrogen is sp2, these electrons here are orthogonal. So those are the concepts, those are the characteristics that we've studied. Let's apply that and see what we should get as an answer for each. This is not aromatic because it does not meet the Hucker rule, because it's 2, 4 pi electrons. This is not aromatic because it has 8 electrons, 2, 4, 6, and 8 electrons that are in conjugation. So it's not aromatic because it fails Huckel's rule. This is aromatic, so because these lone pair of electrons on nitrogen can participate in this conjugation here to make 6 pi electrons, which would meet Huckel's requirement. Here's the other one we were talking about. 2 pi electrons here and none here. Notice none, because the electrons in this bond are associated with that oxygen. So based on this, this is aromatic because 4n plus 2 equals 2 means that n is 0, so that meets Huckel's rule. So this is aromatic. This is also aromatic because we have 10 pi electrons here, and of course, as we said, these electrons here are not part of that aromatic ring. So that's an aromatic molecule. I think this is the last of the slides for this lecture on chapter 17. So once again, continue studying, continue reading up in your text, and the bottom line is to be able to understand the concepts of those 5 characteristics of aromaticity, and equally important is to apply those concepts to solving the problems of aromaticity in terms of if a molecule or a cation or an organoanion, is it aromatic or not. Okay, so continue to study hard. And remember, as I put in most of my emails, that education is not just learning facts. It's not just learning the content, but it's using the information that we are gaining here to train the mind to think, to be analytical thinkers and problem solvers. Okay, continue to study hard.